Okay, good afternoon, everyone, or good morning. So today we're going to talk about the volumetric analysis lab. Okay, so we'll deal with any class questions and things after the recording here. So let's jump right into what it is we're gonna do for this lab. All right, so we're using a simulator for this, and the simulator is similar to the same one that you may have used last time for the solutions lab. So this one is very similar to the same lab that we would have done had we done this in person. Okay, so first let's look at the handout that you have in front, or the handout that you may have in front of you. All right. Okay, so from our handout on volumetric analysis, okay, so this outlines these steps that we would have gone through had we done this in the lab, okay, which involves us using a burette and setting up various solutions and doing the titration. So there are two parts to this experiment. Part A deals with standardizing sodium hydroxide. So a standardization is usually done because we don't know the exact concentration of the solution that we've made. Okay, so in this case, we have prepared a sodium hydroxide solution out of a rough prep. Okay, so we just did the scoops and made the solution, and we know it's about what we want. But if we're going to use things for an analytical purpose, okay, we want to know exactly what its concentration is with as much accuracy as possible. And so a titration is an analytical technique. And so what we would do is we would take the solution that we're not sure about, in this case, in part A is the sodium hydroxide, and we would titrate it, okay, we'll talk about what the titration involves here in a minute, against something that we do know what its value is. Okay, in this case, we use a standard acid called potassium hydrogen phthalate, okay, or abbreviated as KHP, okay, where it is a monoprotic acid, okay, and so we have an acid and a base. And so we know the acid part here because we would have made this with using analytical balances and weighed out exactly the amount that we need. And so we know exactly how much of the acid we're putting into our titration setup. Okay, and then that helps us to determine what is its reaction with the base. Okay, so we have it interacts via this equation here, which is a standard acid-base equation. We have the acid plus the base makes a salt and water. Okay, so we do the titration, and so if we know the moles of this, okay, from our stoichiometry, okay, if we know how many moles of this we have, we can calculate how many moles of this we would have. That's a basic stoichiometry from our balanced equation, right? So that's what we're going to do for part A. Is essentially we're going to use the KHP, which we know, okay, to find the sodium hydroxide that we're unsure of, okay? And then we will do a couple of different titrations, and then that will allow us to get a fairly certain value for what is our molarity of our sodium hydroxide, okay? We would then use this sodium hydroxide that we now know analytically what is its concentration with several sig figs at least, probably three or four, okay, to find the concentration of an acid solution. In this case, it's HCl. Okay, so this is not an unknown. We know that the unknown in part B is HCl. Okay, but we don't know what its concentration is. So this is akin to other experiments that we've done where we don't know what the concentration is. Okay, in this case, we're not using a calibration curve. We're using another analytical technique of the titration. So in part B, we're determining the concentration of the acid solution, okay, of the HCl that we don't know. Okay, so as you scroll down through here, you will see the amendments to the in-lab, to the simulator procedure from what we would have done in class. Okay, so it's it goes fairly well. The simulator goes fairly well with the lab we would have done in person, okay? There are some adjustments. Now, if you don't pay attention to the things in blue, okay, you will not get this right, okay? In the lab, the sodium hydroxide that we've made is about 0.15. The simulator uses a 1 molar solution. This is a drastic difference in the concentration. So so that affects down here to the KHP that we weigh out, okay? In class, we were weighing out about 0.5 grams, okay? But you need to use about 3 grams in the simulator because the base is so much stronger than we used in the lab, okay? So they've scaled, so in the lab, we had a low concentration of base, and so we used a low amount of KHP. But they up the concentration of the sodium hydroxide in the simulator, so we need to up our KHP value for the simulator, okay? So if you don't pay attention to that, then either it'll take like a drop of base to hit the endpoint, which is not going to give you much in the way of information, right? So you need to make adjustments with the blue for the simulator, okay? In the simulator, when we are using what's called an indicator, okay? So titrations use an indicator in order to know when we've reached the point of interest, okay? So an indicator is an organic compound that changes color at different pHs. So in the lab, we would add a couple drops, but the simulator doesn't have a dropper, so you need to use about 0.5 milliliters of the indicator in each one of your solutions. If you don't add the indicator, you won't see anything. Okay, we have this same problem in the lab where you have a clear solution and another clear solution, and I'm pouring clear solution into clear solution, and I'm not seeing anything. It's like, well, you need the indicator in there, otherwise you're not going to see anything. Okay, so we have to prep the solutions with the indicator in it. Okay, and again, we'll get over to the simulator here in a few minutes. Okay, so determining the concentration of the HCl, okay, so is the conclusion for part B and the purpose of the experiment, right? The data table here is pretty much exactly the data table that you're going to need to use, okay? So the conclusion of part A is the molarity of sodium hydroxide, okay? All of these cells here are stuff that you would fill in if we were in the lab, and it's the same stuff you would do if from the simulator, okay? Part B, again, all of this stuff here is exactly as we would do in the simulator and exactly as we would do in the lab. And so the conclusion of part B is the molarity of the acid solution, okay? All right, so let's take a look here at what the calculations and what our solution is going to look like. Okay, so all right. So for a titration to work, it operates on the basis. Now, there are different kinds of titrations. Okay, in this case, we are using a pH titration. Right, so we are titrating an acid. Okay, so we would expect an acid initially to have a low pH. Okay, so as we add, so what we have here is we have in our burette, okay, we have NaOH in the burette. And then we have a flask where we have HCl, okay, or, or the KHP, right? So we are going to dropwise, so we're going to add our sodium hydroxide from the burette, right, into our acid solution, okay? So initially, before we've added any of our base, okay, our pH of our acid is relatively low, okay? As we add a little bit of base to our solution, the pH is going to steadily start to go up. Now, this particular titration that we're operating off of is called a strong acid, strong base titration. So in a strong acid, strong base titration, the endpoint is usually at a pH 7, okay? Because we are making a salt and water, okay? And our salt is neutral, okay? So at this point here, the moles of the acid equal the moles of the base. That's how the titration works, okay? Because of this relationship, okay, we can use, in part A, an acid that we know to find the moles of the hydroxide that we don't know. And then in part B, we can use the moles of the hydroxide we do know to then find the moles of the acid that we don't know, okay? Okay. So all of this is contingent upon the volume of, okay, we are adding volume of sodium hydroxide, okay? So the titration, the conclusion of the titration, this is the important number that you would collect in the lab, okay? How much volume does it take to reach this point? Now the question is, well, how do I know that I've reached that point? Well, this is the point when the indicator would turn pink. Okay. If you have an organic indicator, it is going to turn pink right at this spot. So that's how we know we've reached the endpoint. And so if we're adding from a burette dropwise or in some increment, and we're adding volume in here, we know where we started, okay, the initial volume, and then we would start adding, and then we would wait until it turns pink. Okay. And then we would record the final volume. Okay. And that is really the only data that you're collecting here that we need to know for each one of these values. In order to get the data that we need at the end, we need the initial and the final volume from our burettes. Okay. So you can conduct, since this is in a simulator, it's easy to do 3 titrations and not have this take very much time. Okay. So in part A, we would have KHP as our acid. We'll titrate in order till it turns pink and get the volume. That'll allow us to convert the moles of the H plus to the hydroxide, and then vice versa. All right, so let's look at the calculations now. Okay, now this should follow with the data table. Okay, so this is for part A. Okay, you're measuring out some amount of KHP. Okay, in this case, I believe it asked for 3 grams. Okay, so whatever it was, okay, whatever value it is that you use can be used in the value. Okay, the titration works no matter how much KHP you use, but again, whatever your value is just going to affect the volume of your titration. Okay, so if we know the mass of the KHP we used in our solution, okay, its molecular weight is 204.23. Okay, grams divided by moles would tell me how many moles of KHP I have. Okay, so again, this is something we would have weighed out on an analytical scale, so you have all the decimal places for this. Okay. We know from our endpoint, this amount of KHP is what went into that flask. Okay, so it doesn't change. It doesn't go anywhere. So all of that is what's reacting with the base. So all of that that reacted with the base, we would say is equal to the moles of the base after it turns pink. Okay, so if we know then the moles of the hydroxide, the only thing we really need to know is how much volume did it take to turn pink. Okay, this is your titrated volume, but you have to put it in liters. Okay, the burette reads in milliliters. Okay, so you have to convert your titrated volume to liters, and then moles divided by liters is molarity. Okay, so you should have probably 3 trials for part A, which would allow you to get an average value for the sodium hydroxide. And because we're doing this in a simulator, those values should be relatively close to one another. I don't think the simulator changes its values too much. Okay, so then we move on to part B. All right, let me just leave this here for another second here. Okay. This should follow with your data table. The mass of KHP at the top, the moles of the KHP. All right. There's the steps in there of the volume, right? It has the initial and final volume in there in your data table. The moles of the hydroxide divided by that volume titrated is the sodium hydroxide value. Okay, for part B, okay, we're going to know now the molarity of the sodium hydroxide from part A. Okay, each one of your samples in part B for the acid, for the HCl, are 25 milliliters. Okay, so again, the only real question here is the volume that you use to titrate. How much did it take to reach the endpoint? Okay. This setup is slightly different because here we are working from the strong acid, strong base titration. So here we can use the equation for an acid-base reaction. Okay, this should be hopefully familiar. You have the molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. Okay, so we are looking for the molarity of the acid. We know the volume of the acid, that's this value here, the 25 milliliters. The molarity of the base is the value that we got from part A. Okay, this is what you would get from the titration after you've mixed your sodium hydroxide and your HCl sample. Okay, so again, this thing is going to get set up the same way. You have your 25 milliliter HCl in your flask with the indicator in it, your burette with your sodium hydroxide solution, titrate, initial and final volume. So then you would know the volume titrated. Okay, how much did you put in there? Okay, so we know the volume titrated. So you know 3 out of the 4 terms here. Multiply and divide would give you the molarity of the HCl. The volumes here can be in milliliters. It's fine. Okay, they just both have to be milliliters. Okay, it does not have to be in liters. Okay, because the volumes would cancel each other out. Okay, you do 3 titrations for the HCl, you should be able to get a decent average of what is the concentration of the HCl. Okay. All right, so now we're going to switch over to the simulator. All right. So let's look at the simulator here. Okay, so simulator should be very similar to what we've looked at before. Okay. What you have are all of your stock solutions over here. Okay, so you have your approximate 1 molar sodium hydroxide. We have KHP. All right, you have phenolphthalein. You have your hydrochloric acid unknown. Okay, we have various glassware that we're going to need. So things like we're going to need an Erlenmeyer flask. Right, so we need an empty Erlenmeyer flask. I'm going to do one of the titrations here to walk you through. Okay, so if we were doing, say, our KHP solution, okay, all right, you can put your flask right onto the scale, right, and again, if you hit tare, it does just like the solution would do in the lab. Okay, it would reset your scale back to 0. And then we want to add KHP to that. Okay, now again, there are various ways of doing this, whether we can do this via sig figs or realistic, and you're holding down to pour, but again, that can be slightly a little bit difficult, right? So in this case, probably real, and again, if we were doing this in the lab, it would not come out to 3.00, and maybe you don't use exactly 3.00. Okay, again, maybe you do this a little more realistically and pick some random numbers that are near 3. So 2 point, let's say 956, right? Okay, it's close to 3, but it's not a 3.0, number. Okay, and so we would write that down, and so that would be our number that we would write down for our calculation. 2.9560. Okay, those are all the numbers off our scale. Our scale reads 4 decimal places, so I'd write down all 4 decimal places. Okay. And then we could put our KHP away. Okay. And so our flask here has my KHP in it. Okay. And what we want to do is then we need to add some water. Now our procedure in this case, if we are says to add 50 milliliters of water, you'll find it wouldn't matter if we were doing this in the lab how much water you use, but we could put the 50 milliliters in there. Okay. So again, here, this is a little bit different than if we were in the lab because there's no mixing involved. It's where it already kind of does everything magically. Okay. And then we want to add phenolphthalein. Okay, we need to add some phenolphthalein. Again, here, we can't do this dropwise, so you have to just do 0.5 milliliters. Okay, and we're not going to see anything in this case because the phenolphthalein is clear into acidic solution, so you're not going to see any difference in my sample. Okay, now we would say here that this is KHP sample. Okay, and maybe we duplicate this. All right. So I would actually have probably 3 duplicates, again, my procedure here is very similar to how I would recommend doing it in the lab too, is where we have one that's kind of a throwaway, where we're just doing our first one just for, to see what it looks like, right? So if this is our first time doing a titration, it's often not something that you've seen before. So we want to know, what is it going to look like when I do this? Okay, so we want to get that's under other, the Burette. Okay. And we're going to put our about 1 molar sodium hydroxide. Okay, so we're going to bring that over to the burette. And then it says, well, how much do we want to put in there? Okay, if you put 50 milliliters, it's not going to fill it up all the way because there is a little bit of volume at the bottom that's kind of unaccounted for. All right, so if you really want to put it at 0, right? All right, so let's take another look at this. All right, this is important here, and this is something I would highlight in the lab. A burette is 50 milliliters, but you read the volume that is there. So when this is full, the initial volume is not 50 milliliters. Do you see a 50 right here? You wouldn't, okay? The initial volume, where the bottom of the meniscus is 0. So your initial volume is 0. And it's not just 0, it is 0.00. You can read between a 1 mil, this is a 0 and 1 milliliter. And so you can see there's 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1 milliliter. So there are 0.1 graduations on a burette, which means if it was in between 0.4 and 0.5, I could see that it would be in between 0.4 and 0.5. And so I would have to estimate, what do I see as the last digit? Okay, remember, we can always estimate 1 digit more, 1 decimal place more than the graduation. So you should be able to get 2 decimal places off of burette reading. Okay, this should be how you should use the sig figs for a lab, for your burette from this lab, regardless of if we're doing it by simulator or not. Your sig figs should be 2 decimal places for the burette readings. Okay, all right. So we have our burette is prepped and ready to go. We have added our sodium hydroxide to it. We have a prepared KHP sample. Okay, I have dissolved my KHP into 50 milliliters of water. I've added my indicator. I have everything here that I need. The volume of the KHP sample is not important. Okay, how much is there is not important. It is the moles of stuff interacting. So here you bring the burette over to the flask. All right, or maybe I always forget, like, is it easier to bring the flask over to burette? No, that doesn't work. All right, so you want to set the flask down at the bottom and bring the burette over to the flask. Okay, there we go. So it is easier to set the sample at the bottom of the screen and then bring the burette to the flask. All right, that gives you all your room here. Okay, so again, this first sample, you notice I have 4 samples. All right, this first one is just a throwaway. Okay, I want to know about when it's going to turn pink. I don't even know what this is going to look like in the simulator. I've never used this simulator before, or presumably you haven't. All right, I've done it before, but you haven't. So we don't know what we're looking at. Okay, what is this going to look like when I start adding stuff? Okay, so I'm going to put 1 in there for a milliliter. All right, now if I hit pour, okay, you'll notice the volume drops on the simulator. It goes from 0 to 1. Okay, added a milliliter. Well, let's keep going. Another milliliter, another milliliter, 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 milliliter. We're adding stuff in there. Now, presumably, if we were in the lab, there would be some point where people catch on the fact that they did something wrong because nothing happens, or then I get the raised hands of, Dr. Jensen, nothing happened and we've emptied out our burette, and then I have to, go back to the fact that if it gets down towards the end, okay, at the 50 milliliter part, don't keep going. Like, stop before you hit past 50 milliliters, because if you drain it past the 50 milliliter mark, you basically have to start all over again. Okay, if you stop before the 50 milliliter mark, you could refill it and then keep going. Okay, but we don't know where our titration is going to end, so we're just, oh, there we went. Okay, and in the simulator, it turned pink at 16 milliliters. Okay, but this is a crude amount. We were just doing it by 1 milliliter increments. You wouldn't do that if we were in the lab. We would not, if you're doing, you do your throwaway titration at a larger increment, just so we can know where the endpoint is. Okay. So my initial was 0. My final is 16 milliliters. Okay. So I record that down. So I know now that my sample, okay, should take about 16 milliliters. Okay, but so this would be my first real sample. Okay, so I know it should be about 16 milliliters. So what I want to do is I just don't want to use 16 milliliters. I want to go slower towards the end. Okay, so my initial volume here, you can get more than one titration out of a burette. You don't have to refill it. Okay, so my initial here is 16.00 milliliters. Okay, and so I'm going to add 14 milliliters and see what happens. Okay, I added 14 milliliters and nothing turned pink. Okay, now this would be usually the time where we've added a bunch to it, and we want to now go in a more precise amount. Now, then if we were doing this in the lab, I would say this would be the point where you would do it dropwise. Okay, you want to turn it on to where you can put a drop in, but it's slow enough that you could turn it off in between drops. Okay, so we can choose our volume here. So again, the milliliter, it reads in 0.1, so 0.1. Okay, now watch when we do this. Okay, that's a 0.1 increment. Okay, and there it went pink. Okay, now you notice the pink color is slightly different than the other pink color. That's this is the pink that you really want, is a very light pink. Okay, so I would say 16 milliliters is my initial, 30.40 is my final volume. So 30.40 minus 16 is my volume delivered. Okay, now if we keep going, now you see it gets a little darker. And say the 0.1 milliliter is the difference there. Okay, so you saw we hit it precisely. The precise value that you're looking for is when it's a light pink. Okay, which is very cool that the simulator gives you this option. It just doesn't go to pink. You can get it exactly to where it's a nice light shade of pink that you know you've hit the right value. Okay, so now at this point, I've probably used too much of my burette, so I would need to refill it, right? And so we refill it. Okay, so you keep using the sodium hydroxide to refill the burette. Okay, sample number 2. Okay, and we know from the first sample how much it took. The 16 milliliters minus the 30.4. All right, so you can do, the 14 milliliters, and they do it by 0.1. Right, and pretty consecutive value, right? Record initial and final volume, right? Etc. Okay, sample 3. 14 milliliters. 1. Boom. All right. 3 samples, average the values, or calculate the KHP's concentration, or the moles of KHP in your 3 samples, which theoretically at this point would all be the same moles because you only used 1 sample and we just duplicated it, right? So my volume's titrated, which then would give me an average value of sodium hydroxide, which again, theoretically should be the same number for your 3 trials, presumably. Okay, refill your burette again. Sodium hydroxide stays in the burette, but then your next sample is the HCl sample. Okay, here's your HCl that we don't know, right? That has to get transferred into one of these flasks as well with the indicator. Titrate again. Okay, so these samples would get discarded. You would need a new flask, right? We're putting Now, again, this is one of those things where from the solutions lab that we did, that I griped on people about their procedure, is that it doesn't quite work this way of taking this sample and just pouring it over here. I mean, yes, virtually I can just do this and have it do 25 milliliters, right? But in the real world, you can't just pour into a flask and get 25 milliliters. Okay, that doesn't work in the real world. You have to actually use an actual piece of glassware that measures 25 milliliters, right? So you would have to use a 25 milliliter graduated cylinder to first get the 25 milliliters if we were doing this in the real world, right? And then that sample is what you would put in here, because this flask doesn't measure 25 milliliters. So there's no realistic way that you would get this in here and get 25 milliliters, okay? The flasks are not meant to measure volume, okay? Their graduations are very imprecise, okay? Again, the simulator makes this a little easier because it's a computer and it'll do what you tell it to do, okay? But in the real world, you can't get, so what people were telling me is like, oh, I'll just take, from this 2-liter jug, just measure off, 22 milliliters into the flask. Well, but the flask, how do I get 22.5 milliliters into this flask? You can't get exactly 22.5 milliliters into this flask, okay? You would need to use a graduated cylinder to measure out the volume first, okay? So if we measure out our volume and then add some phenolphthalein to it, again, 0.5 milliliters for the phenolphthalein. Okay, we have an acid sample that's ready to go. Okay, we connect our burette to our acid sample, titrate again. Okay, again, you can duplicate your acid sample a few times and conceivably your values would be relatively close to one another. You can then average and calculate the molarity of the HCl. Okay, that is the purpose of this experiment. I want to know what is the concentration of the HCl sample. Okay. Now, specifically for this lab, you could enter in your answer down here at the bottom, okay, to check if you were right. Okay. The solutions lab, we weren't following the simulator precisely, so the value that you would have put at the bottom is not exactly the value that you would have gotten. But in this case, we are trying to find what is the concentration of the HCl. So your value that is right here is the, you can put this in here and check to see if you're right. Okay, and so this is a full lab write-up, just like normal. Title, purpose, procedure, your data section with the pre-lab questions, and a conclusion. Okay, the purpose of the experiment is to determine the concentration of an HCl sample. We are doing this via titrations. The concentration of your sample is what? Okay, so that is it for the simulator. So we will stop here and I will be open for questions.